So welcome back everyone. In this set of recording, total of 4 records, we will be covering topic number two, which is flexure capacity of beams and one-way slabs. As I mentioned, topic 2 will be flexure capacity. We will focus on analysis and design of beams and one-way slabs. This will be covered by our textbook from chapter 2 to chapter 5, so chapter 2, 3, 4, 5. In-class lectures will be 6 lectures of 1 hour 15 minutes. However, we will be covering this topic in the recording for 4 different videos. So to start with flexure capacity of beams, we need to really understand the difference between fibers. If you have fiber in a cross section, and also the difference between the fibers and treating the entire cross section with reinforcement, and also the difference between that with elements, so such as a beam. So fibers, if group of fibers create cross section, group of cross section stacking side by side create an element. In the fiber level, this fiber is made of material, either reinforcing steel or concrete, and we will be interested to know what is the stress strain curve of this material. So this applies to finite fiber. A group of fiber, as I mentioned, create suction, and the suction actually will be interested to know what is the moment curvature. And a group of sections will create an element, or in this case beam, and we'll be interested to know the force displacement relationship. So we will cover a key moment and corresponding curvature here. As you can see, we will have introduction. We will know how to calculate the cracking moments. So the moment that as concrete starts to crack at, which is related to modulus of rupture, as we covered in topic number 1. We also going to know how to calculate elastic stresses for concrete when concrete is cracked, which is basically the region between M crack and M yield. Part of this region, we call it service region, where the actually working load is applied. And we also going to know how to calculate ultimate or nominal flexure moments, which is basically upon failure of the cross section. So to start with, we will cover what's stage called uncracked concrete stage. In this stage, there's key assumptions. The first assumption will be tensile stress in concrete are less than modulus of rupture. So you know how to calculate modulus of rupture from before. If R is or equal to 7.5 lambda square root of F prime C. So calculating the stresses related to modulus of rupture, you can actually make it equal to tensile stresses in the concrete, and this assuming that this is a stage where the concrete will start to crack. The entire beam cross section resists the bending, so there is no, because we have assumption that we don't have cracks, and compression on one side and tension is on the other side, and the entire cross section, as we mentioned, is resisting the moment. And as you can see here, the modulus of rupture equation for ACR and ACI, FR equal to 7.5 lambda square root of prime C. And on the right side of the slide, you have a concrete section reinforced with rebar. And you can see here we are drawing the stress diagram. It's very similar to a structured steel before yielding. You'll have extreme fiber in compression, and this is a strain, corresponding strain, and extreme fiber in tension, and this is a corresponding strain in tension. And you have a straight or linear relationship, and here at this level when you have reinforcement, you can also get right away the strain in the reinforcing steel, epsilon s. Moving to stresses. So the first part, the strain, is called the compatibility of strains in the cross section, or compatibility principle. However, the stresses can be actually estimated too. So the same relationship, linear relationship, we have a stresses in concrete and compression, and stresses in concrete in tension, and stresses in the rebar or reinforcing bar in tension in this case, and it will equal to this Fs divided by N, which is a modular ratio, as we're going to cover later. So still in the concrete crack section, with moving from a crack section to an uncracked section to crack section, so concrete start to develop hairline cracks or some cracks due to loading and not able to resist the tension forces. When that happens, when tensile cracks start, actually neutral axis move upward, as you can see here. So the linear is not symmetric anymore. The relationship for strain, stresses are no longer linearly related to strain, as we mentioned before, and reinforced bars will also yield. As you can see here, since if your neutral axis is at this level, all the concrete in this area below the neutral axis, all the fibers crack, and you're only going to have the reinforcement that can carry the tension force, oftentimes to be yielded, and you'll have the concrete compressive stress here. One major item or metric that we need to know is curvature. Curvature is the slope of the strain in the strain diagram, or rate of change of strains per depth of the cross section. So this is what we call phi or theta. So theta is angle change of beam section over length, which also correspond to the rate of change of strains. So it's basically strain divided by distance. In this case, this is going to be the strain, and this is going to be the distance. And here again, we are showing the moment curvature diagram. You have the cracking moment, which separates a state where concrete is not cracked and a state where concrete starts to initiate cracks. You have surface moment, which is part of the curve between cracking and between the yielding. Here is a point where the first onset of reinforcing bar yielding, and here is the maximum moment, which we often correspond to nominal moment or even ultimate moment if we apply the resistance factor reduction. Here, in order to calculate the cracking moment, it's a very basic equation. Relation between bending stresses to bending moment is stresses equal m, the moment, times y, which is a distance from neutral axis to the fiber of interest, either tension or compression, divided by I gross, which is the entire inertia of the cross section. So this applied only if the concrete is not cracked. At onset of cracking, you can use M and make it equal to M crack, but you need to know that this happens only when F stresses equal FR modulus of rupture. So here we are rewriting the equation similar to ACI 24.2.3.5, where M crack equal FR times IG divided by YT, which is the rearrangement of this equation. Need to know that ACI equation 19.2.3.1 FR modulus of rupture equals 7.5 lambda square root F prime C, where lambda is parameter related to either concrete is normal weight or lightweight concrete. So if normal weight concrete, your lambda is 1. Sand lightweight concrete, lambda is 0.85. Lightweight concrete will be 0.75, all lightweight concrete. Again, recalling the equation here, to calculate M crack, your equation will be according to ACI 24.2.3.5, where FR times I gross divided by YT equal to your M crack. Let's go to an example here very quickly. This example will illustrate the equations that we previously mentioned. Assuming the concrete is uncracked, so this read carefully. So we are before the cracking moment. Compute the bending stresses in the extreme fiber of the shown beam for bending moment of 25 foot per kip or kip per foot. Kip foot, sorry. The normal weight concrete has F prime C of 4,000 psi. So it's normal weight concrete, so lambda equal 1, and F prime C is 4,000, and the moment is 25 kip foot. And your cross section is 12-inch wide, 18 total depth, structural depth 15, which is the distance from the top fiber to the centroid of the reinforcement, and 3 inches of cover, and we used 3 number 9 with total area of 3-inch square. So first of all, you need to calculate Y, FR, and I gross. So in this case, I gross is a rectangular section. We all know that the cross section, the inertia of rectangular section around its neutral axis is ph cubed divided by 12. In this case, p is equal 12, h is equal 18. So you can calculate right away the R gross or inertia of this cross section as 5,832 inch to the power 4. Using the equation for stresses, my divided by I gross, m in this case is 25 kip foot. To convert it to pound foot, you multiply by 1,000. You convert it to from feet to inches, you multiply by 12. Y in this case equal 9, which is h over 2 because the entire cross section is intact, 9 inches. And we calculate I gross already before as 5,832 inches, so you get the stresses of 463 psi. So this concrete experience stresses in tension, in the tension side and in the compression side as 463, while it can actually prime C is around 4,000 psi. So it's almost 10% of the stresses or less. Second part of the equation of this example 1, will be determine the cracking moment of this cross section. So we previously calculated I gross. We know Y as 9 inches. All we need to calculate now is FR, and we know it's 7.5 square root of F prime C, given that lambda in this case equal 1. So this stresses, if you calculate using a prime C of 4,000 psi, is going to end up 474 psi as modulus of rupture. Use the equation from ACI, M crack equal FR times I gross divided by Y, and we just calculated FR as 474. I gross was 5,832 inch to power 4, and Y is 9 inches. So this will get you a moment of 25.6 kip per foot, which is slightly more than 25, which was mentioned in part A of this problem. Moving from cracking moment or moment below cracking, our stresses below cracking to stresses, actually elastic stresses, when concrete cracks. So in this assumption, we have some assumption here that you need to know. All concrete in the tensile zone is cracked and is negligible or is neglected. So if this is your neutral axis, all concrete below the neutral axis is cracked, and the only function of the reinforcement is to host, the concrete is to host the reinforcement and to have better bond with the reinforcement, so the reinforcement can carry the tension force. So perfect bond between the tensile steel and concrete is assumed. Strains in two materials are equal. Okay, stresses are not equal because different on modular ratio, and the modular ratio here is the ratio between steel modulus of elasticity to concrete modulus of elasticity. We have concept called transformed area method, where you convert this cross section to an equivalent concrete section. We know below the neutral axis concrete is cracked, above neutral axis concrete is intact and can carry compression. So this is going to be the rectangular section. However, the reinforcement has to be converted to an equivalent area of steel. This by concrete, this by multiplied area of steel by the modular ratio, and which is a ratio between modulus of elasticity of steel to modulus of elasticity of concrete. Strain here easy. Concrete will experience stresses in compression. However, the stresses here will be Fs from steel divided by N for this equivalent transformed area. So if you go to an example very quick, there's two parts of this example. I will say part A and part B. In part A, calculate the bending stresses in the beam using transformed area method. Use concrete strength of 3000 psi, modular ratio N equal 9, ratio between ES and EC given right away, and moment of 70 kfoot. The cross section is 12-inch wide, 20-inch total depth, 17-inch structural depth, 3 inches cover area of steel is 3 inch square, and this is your transformed section. You know that it's going to be rectangular, there's going to be X distance here, we don't know it, and the width here is the same given 12. And the distance between the neutral axis to the equivalent area of reinforcement will be 17 minus x, which is the structural depth d minus x, and this equivalent area for steel reinforcement will be n times as, which is 27 inch to the power 2. The second part is actually calculating the allowable bending moment if I give you the stresses as those numbers. So we'll discuss that after we finish calculating the stresses first. So here we need to calculate basically what's called I cracked, because your section now is transformed. In order to calculate that, you need to calculate what is X. So X is will be defined actually by taking the moment of area of the two parts of the section around the neutral axis. So if you take the moment of inertia of this rectangular around the neutral axis, which is the edge of the rectangular, not the centroid of the rectangular, the moment will be bx cube square, divided by 2. So the moment of area is x times p, and the centroid of this one is at x over 2 from the neutral axis of the cross section. So you multiply px times x divided by 2 and make this equal to The area here is NAS, and the arm or the distance from the neutral axis of this area to the neutral axis of cross section is D minus X. So if you plug in those numbers, B you know it's 12, X is unknown, times X over 2, which is still X unknown, equal 27, which is NAS, multiplied by 17 minus X, which is D minus X. Rearrange this equation and solve for X. X will be 6.78 inches. Now calculate the inertia, which we call I crack in this case, where I crack is a crack's moment of inertia. Now you take the moment around neutral axis, given that you know now X's, right? You know that the moment of inertia around any rectangular section, for the rectangular section around its edge, not around its neutral axis, and in this case the edge is our neutral axis of the cross section, is equal to bx cube over 3, and for the other part will be NAS, which is the area, multiplied by D minus X squared, which is area times square of the distance between the local neutral axis to the section neutral axis. So by plugging those numbers here, I crack will be equal 1 over 3 times B, which is 12, times X cubed, which is 6.78, plus 27, which is NAS, times 17, which is D, minus 6.87 square, all square. I give you a cracked moment of inertia of 4,167 inch to the power 4. Now we have I crack, and you now have the x's and distances. Now you can calculate the stresses. The first one will be the same equation, my over I, the general stresses equation. In this case, moment is given as 70 kip foot. Y is in this case either x if you calculate the compression stresses, or 70 minus x if you are calculating the tensile stresses, and I will be I crack. So let's calculate first the compression stresses. Compression stresses will be equal M X divided by I crack. M is 70,000 pound per foot times 12 to convert it to inches, time X, which is given as 6.78 inches, divided by I crack, which is 4,167 inch to the power 4. It gives you 1,400 psi of stresses. If you want to calculate the stresses in the rebar, it's going to be similar. This would be in the concrete side, M times D minus X divided by I crack, but since now we have to convert it to steel, we have to multiply times N. So N is equal 9 modular ratio. Moment is 70 kip feet, sorry. So 70 kip feet times 1,000 make it pound per foot, pound foot, and multiply by 12 to convert it from feet to inches, and D minus X is 17 minus 6.78, and divided by 4,167 inch to the power 4. That give you actually stresses in the rebar of 90,000 psi. Here you just need to compare it very quickly to F prime C of, in this case, was 4,000 psi, and the stresses here in the steel is yield stresses or strength is around 60. So you are around third of the yielding, and you are around almost third of the F prime C. So let's calculate now the moment. The moment will be the same equation, but you rearrange it when you give you the stresses. So it either give you stresses to calculate the moment, or give you moment to calculate stresses. So in this case, the first stresses were 1350 as compression in concrete, and this just use this equation is 1350 times 4067 divided by 6.78, which is originated from this equation FC times I crack divided by X, and this gives you a moment of 67.5 kb foot. If you go to the other side, the tension side, the problem gives you the stresses as 20,000 psi. So the rearrange equation Fs times I crack divided by N times D minus X, it will be your moment at tension side. If you plug in the number, N equal 9, D minus X is 17 minus 6.78, which is 10.22, and I crack is calculated earlier as 167 inch to the power 4, and the stresses given was 20,000 psi. This gives you a moment of 73.7 kfoot. So you actually calculated first the moment needed to generate stresses in concrete, compressions in the top fiber, compressive stresses of 1350. Okay, and this happened to be 67.5 kb foot, and to generate 20,000 psi in steel, you need moment of 73.7 kb foot. So they yield to be not the same number. So in this case, the critical moment will be the least of the two. So you will reach 1350, but you reach less than 20,000 psi in this case, because if you use 73.7, you will reach 20,000 psi, but however, the stress will be much higher in the compression side. So we usually use the least of the two, which is 67.5. So to calculate the ultimate moment or nominal moment, tensile bars are stressed to yield before concrete crushes. This is the main assumption. First of all, you will have a cross section like that. B is the width, D is the structure depth, distance from the top fiber to the tensile tension reinforcement, AS. And as you can see, we know that above a neutral axis, concrete will resist the compression. Below that, concrete will be cracked. So if yield will initiate under reinforcement, and this is going to be part of the stress strain curve of this concrete that we usually draw, will be here on a distance C, where the peak here value will be F prime C. Because now it's going to be very difficult to calculate this area. There is a Whitney block or Whitney stress block that is used to convert from this stage to this stage, where C is reduced to B and E, which is beta 1 C, where beta 1 is function of F prime C you are using. And the area, so now is instead of distributing stresses over C, we are distributing over A. And also we're going to use 0.85 F prime C to get an equivalent area here to this curve here. And now we can calculate the forces. The first force will be the tension force, T capital, which is AS, area of steel times F yield. And area of the concrete here will be stresses times the area of the concrete in compression. In this case, A is the depth of compression and B is the width. So the area will be AB. And the stresses is actually 0.85 F prime C as we discussed here. So you have to make sure that C equal to E to reach equilibrium, and the moment generated will be the torque between, or the distance or arm, distance between forces times either C or T, times the arm, and in this case arm is D minus A over 2, as you can see here, because the centroid of the force C is at A over 2 from the top, and the distance from the top for the tension is D. So the arm will be D minus A over 2. So, and you have to know that beta 1 is actually function of the F prime C. So to solve this problem, which is example number 3, calculate nominal flexure strength. So it's nominal strength for the beam if the yielding stresses is 60 KSI or 60,000 PSI of reinforcing steel, and the strength of concrete in compression is 3,000 PSI or 3 KSI. Again, for cross section of 14 inch wide, 24 total depth, but structural depth of 21, an area of steel of 3 inch square. Now we get the Whitney block. The concrete height in compression will be A, which is 0.85 C, because we can discuss this next lecture, but let's focus on A now. And the height of stress is 0.85 F prime C. So now we can start calculating the tension. Tension equal AS F yield times F yield. F yield is given as 60 KSI. AS is 3 inch square. Now you got 180 kips as tension force. Compression is 0.85 prime C times area of compression, which is A times B in this case. So it's 0.85 times 3 times 8 times 14 and give you 35.7 A times A. A is unknown. You have to make T equal C to get equilibrium. So 180 kip equal this kips equal 35.7 A. A in this case will be 5.04 inches. You got the arm is D minus A over 2, D equal 21, A over 2, A will be 5.04 divided by 2. That's going to give you 18.48 inches. Moment or nominal moment will be force C or T. T is easy because we calculate it as 180 kips, times the arm, which is D minus A over 2, which you get 18.48. You calculate that, you get 277.2 kip foot. Another example, example number 4. This example a little bit tricky because you have two different widths and a lip here. So stress is the same. Concrete 3,000 psi, steel yielding is 60,000 psi. That area of reinforcement AS is 4 inch square. The bottom width is 18, top width is 6 inches, depth of lip is 6 inches. Distance from this level to the reinforcement is 15, and you have cover of 3 inches. So if you understand the same concept that you have tension and compression, you will see that the tension is easy to calculate as ASF yield. It is 4 inch square times 60 KSI, give you 240 kips. Okay, and the C, which should be equivalent now to T, is 0.85 F prime C AC, and usually in your rectangular section it's going to be A times B, but since we are not rectangular section now, we have a variation of the width. Let's call it AC. Let's make A is T, force is equal, T equals C. So the AC unknown now will be the tension divided by 0.85 F prime C. You have your T value is 240, your F prime C is 3 KSI in this equation. You apply, you need area of concrete of 94.12 in order to resist the compression to be equal to the tension. Now you can assume the distance A here as before, but the area of concrete will be equal 6 times 6, which is this area of this small square, plus A minus 6, which is this height. Is going to be A minus 6. This A minus 6 is this distance, times 18, which is the width here. This is going to give you A of 9.23, which is the total height here, A. Okay, so you get the forces, you got C and you got T, and you got actually the layout of the compression in the cross section. Now we have two actually areas. One is 6 by 6. Another one is 3.23. Forget my drawing. Maybe the lighter gray and darker gray here, you can see that the area here is equal to 36, 6 by 6. And if we take the moment around the top fiber, this is going to be 6/2, which is 3 inches. This is 6/2. However, the other area here, the darker gray, will be 18 times 3.23. So this is, can say 18 times 3.23, and the centroid is a distance 3.323 divided by 2 plus 6. So 6 plus 3.23 divided by 2. And if you divide those by the total area, you will get the y bar, the centroid of the compression, which here at a distance 5.849 or 5.85 inches to be approximate. Now your compression centroid is here, your tension centroid is here. So you now use d minus y. Your total d is 6 plus 15 is 21. And your y bar, or before was a/2, now is y bar, it's 5.85. You end up having 15.15 inch as r. Your moment is equal T or C, they are equal, times arm, which is 15.15. That give you 303 kip. Thank you for tuning in this first part of four recording series for flexure capacity.